Welcome to CS 1033 Programming Fundamentals module, and we will discuss the problem solving and programming lecture. First of all, the contents of this lecture is structured to discuss the difference between programming and software engineering, which is done by basically programmers and software engineers. And then we'll look at the process for the stepwise algorithm development, and we'll discuss different steps that help us come with a solution to a problem, and to help us deal with complex problems that we as engineers face. We'll discuss couple of techniques for modeling a problem. One is abstraction, other one we call as computational thinking. If you look at computer science, at the core of computer science is the task of solving problems. Now, these problem solving through computer engineering should result in solutions which are having these very important properties. They need to be efficient in terms of using resources, time, and any other physical resources, the effort, all of these resources. There must be efficient use of such resources in the solving of the problem, and it must be effective. The solution should meet different requirements, like the outcome must be available when it is required, not later. The outcome must be repeatable. So if you are repeatedly doing the same thing, using the solution that we have given to your problem, the outcome should also be the same. And the solution should be economical over the longer term. When you develop a solution, initially it might be costly, but as you keep on using it, your cost of using this solution should average out to a reasonably affordable cost. So computer engineering is the approach we have, the engineering discipline for developing solutions with these kind of properties. Now, what are these problems? So, I mean, it is kind of a list that you cannot enumerate within a period of time. It's very lengthy. I just took as an example, I just took the image of a city, and there are a lot of problems in a city like this. For example, you have a lot of buildings, and these buildings should be managed efficiently. The security of the building, the supply of power, communication, water, crowd control, others, different services. So all of these are managed by what is called a BMS, a building management system, which has elements from civil engineering, electrical engineering, mechanical engineering, electronics engineering, and all of them are put together through software that comes from computer engineers. If you look at the transportation network that is shown here, the expressways, the train tracks, highways, all of these need to be managed efficiently so you don't have gridlock, and the traffic keeps moving, and you prevent accidents happening. And if you are charging for the use of, for example, the expressways, then the toll collection and display of signage, warning messages, all of these. So all of that is handled by software actually, and you can see other fields of engineering play a major role here. The civil engineering to build the expressways, electrical engineering to provide the power, the telecommunication to provide the communication in that, and of course the vehicles from mechanical engineering mainly like that. So, but all of these things are glued together to build an efficient transportation system through software. So the problems that we are given as engineers to solve using software tend to be very complex, of very large scale, and is domain driven. So, transportation domain, building, civil construction domain, and it could be healthcare, industry, education, electricity grid management. So, so depending on the domain, there needs to be some domain specialty required to come up with solutions. Okay. In here, we are going to look at basically what a programmer would do in developing these solutions. So whenever we talk about programs, we have to talk about software engineers also. Okay. So the way, as noted here, the way beginner level programmers would go about solving a problem would be vastly different to what an experienced software engineer would do. Okay, the kind of tools they use, the kind of methodologies they use, they are all going to be quite different. Now, when you specifically look at the software engineers, which is from the computer engineering discipline, they use well-developed methodologies that allow you to start with a problem and work towards a solution that meets the meets a very lengthy list of requirements from whoever the client that gave the problem to the engineer. Okay, and different parts of the solution development process, which we call the software development life cycle or software development methodology, would use different techniques, because there are different type of tasks to perform in these different stages of a solution development methodology. For example, first of all, you have to analyze what the problem is. Thereafter, you have to very carefully document your analysis, which we call a specification. And based on that specification, which is a document that tells this is what the customer expects ultimately as a solution to the problem, you develop a solution which is a design. Okay, so design work is central to any engineering discipline, and so it is the case for computer engineers also. Then this design is implemented. Okay, so it is at this point the term programmer actually comes into the picture. Okay, and of course, this development process, the programming work has other sub areas. You have to test your program, and once the solution is available after the software developed, the programming, the implementation of the design, you will deploy this. And once you deploy, means you install it into the hardware and you train people, you get the users to use it. When this happens, generally there will be request to maintain this system. Okay, so as programming, we are going to look at only a tiny part actually of the software engineering process, which is engaged by software engineers. Nonetheless, it is a very important part, a critical part. In fact, in software engineering, this programming work is fundamental. So without a good base in programming, you cannot do any of the other tasks well, whether it is analysis, specification, design, testing, or maintenance. All of these tasks requires you to have this very important foundation knowledge. Now, the programming that we are going to discuss will look at these core foundational knowledge that you need to gain. The development of solutions to more and more complex problems requires the use of an increasing range of tools, and also you have to carry out a lot of research to understand what the problem and how to solve it. When you take this field of software engineering, research forms a large part of solution building work. You have to use a lot of theory as well as past knowledge on similar projects or related projects to study deeply to come up with a good solution. Now, as our focus is the beginner level programmer, we would normally start understanding a problem and developing a solution as a human would do. Okay, the tools used are limited. Here, generally, the tool is your imagination, your ingenuity, any skills and knowledge you have gained so far. So, as you know, humans have a very powerful computer, the brain. So don't think that just because we use quite a human-centric approach to solving the problem, that it is any less important or that it is a solution which is not really good. No, most of these solutions are really good solutions that we are able to build. So if we look at this solution building, the process which we call algorithm development, okay, we would see the initial understanding of the solution, which comes from the study of the problem, to be quite disorganized, okay, or what we call as unstructured. So we have an idea how to solve the problem, but the more we think about it, the greater the problems we see in that. So because the solution is not really well structured to take care of different issues that come up, as well as the outcomes may not be as precise as we want. Okay, and the process to improve this solution is generally repetitive. Okay, so you would come up with the initial solution, and then you study that solution and make corrections where there are errors, and where there are improvements possible, you will make it an improved version. So this improvement of your solution in iterative manner is aided by your understanding of the problem. So the better you understand the problem, the better your solution would ultimately turn out to be. So when we call a solution an algorithm, generally it has reached that stage of a well-structured and a precise solution. Okay, so initially we would call it our solution, but when we see that it is now at a level where the solution is well-structured. So how do you know the solution is well-structured? Well, for one thing, you can easily understand the solution. Second thing is, when you test your solution, you find that it gives correct answers. So that point, we would be able to call our scheme, our solution, as an algorithm. Okay, so as noted here, these algorithms must be available to us at a level of detail or level of simple instructions that a computer can carry out. So so it is important to note that we when we start developing solutions, initially we will have a solution to a problem that looks very intuitive to us, looks like a really good solution. But through this iterative process, we will ultimately end up with an algorithm. As I said, the algorithm is the final solution, which could be vastly different to what we have started with. So that is to be expected. There is nothing wrong in ultimately coming up with an algorithm which is quite different to the original solution you thought about. So in thinking about problem solving, you must get into this mindset, okay, of developing a precise and structured solution, starting from maybe a quite unstructured and imprecise solution. So to make it easier for you to understand, I thought of discussing a problem that is quite common, okay, finding a path. Okay, so here I have a map, as you can see. So if you want to go from University of Moratuwa, which is in Katubenda, to Colombo, okay, so there are different routes available. You can go towards Katubel Junction and then take the Gold Road, or you can go towards Piliandala and take what is called the Colombo Horna Road. In fact, from there you can even go towards Kottawa, and then get into what is called the high level road, the Avisavela Colombo Road. So this is actually a road network, and not only that, when you are going in these roads, there are interconnecting roads where you can switch from one of these main roads to another road. Now, but of course, what you want to do is go from the university to Colombo, and so which route to take? Which route to take? So this is this would look very simple. So you would look at this visually and see, okay, maybe the highlighted road is shortest distance. Okay, now that may not be the case, because there may be a lot of other sub roads through which you can interconnect and shorten the length. Now, if you really look at it, you can create a you can enumerate all these paths, possible paths, and take the distance and create a table and decide which route is the shortest and then take it. But you might have other criteria. It is not just shortest route you are looking at. Maybe you are looking at shortest time. Some of these routes are heavily congested in certain parts of the route. For example, this part may be congested. So if you are thinking of avoiding that, you may want to take a crossroad to another path, and maybe later join into the original path, because maybe in here it is again congested. So now you can see the solution that you initially thought is not good enough, because you have other requirements, like the time required to go from the university to Colombo. Now, apart from these distance and time, you may have other conditions. For example, if we have tollways, there will be a charge that is that you have to pay for a certain part of the road usage. So if you want to minimize that cost, again you have to look at the alternate paths. So hopefully you get the idea that the finding a path is not that straightforward of measuring the distance. you have to have other data. Now, this is just going from one point to another. Suppose you want to go from the university to town hall, then you will have to again redo this computation. Okay, and if you look at the some of the parameters, like the distance does not change depending on the time of day, but the congestion changes depending on the time of day. And if there are toll roads, the charge may also change depending on the time of day or some other criteria. So it is not meaningful to actually create a static solution saying this is the best way to go from university to Colombo if your requirement is to get there fastest. It is not really a correct answer ultimately. So so the answer is not precise, okay, and the answer is not well structured if you are going to keep lists like that. Okay, so from computer science, we can develop a solution which is to represent our road network as a graph structure. Okay, so as you know, graphs have nodes, and these nodes, or what we call vertices, are linked through these edges. Now, all these junction points where other roads are connecting up, we can mark as these vertices or nodes, and the road segments will be the edges or the links in the graph, and then we can put different values to these links, indicating the cost, the distance, the level of congestion, and then come up with an algorithm, mind you, an algorithm that means a more precise solution, which when given an origin and a destination will compute a path dynamically which is meeting your requirement. Maybe it is the fastest time to get there. Okay, so it will look at all these link cost, for example, congestion cost, and will develop a solution. So this is just to give you an idea, okay, how one would go from a problem to an initial solution to an algorithm, which is a more precisely defined solution. Now, I have here a sequence of steps that you can use to aid in the development of an algorithm. Okay, so first of all, we need to get a description of the problem, and then we will analyze the problem. Okay, this step 1 and step 2 in software engineering we term as specification and analysis. Okay, so you specify the problem and then analyze the problem, and then you do a design. So this design will give you a very high level algorithm. Okay, and then the algorithm is refined. Okay, that means improved. Generally it is done in a iterative manner using different techniques depending on the problem domain. For example, now in the domain of pathfinding, graph theory is a widely used technique. Okay, but graph theory is used in many other things also. Okay, for example, if you want to map terrain, okay, that means get a map of the surface, which is where the surface is irregularly structured. You can take the surface and convert it into triangles. So it's called triangulation, and these triangles would form a grid, which is a graph structure. So like that, depending on the type of problem, we will be using different techniques. Okay, and finally, we have to review the algorithm. So review the algorithm means we have to test it to see whether it is giving us the correct answer, and also whether it is meeting some of the criteria in terms of amount of resources being used, the time it takes to solve a problem, the amount of say what we call memory, because we are running it in a computer, the amount of memory required to run this program. And also there is the other aspect of the data we have to input and how much of pre-processing of data we have to do. Okay, sometimes the data we can just give as we get them. Sometimes you can't do that. You may have to do additional processing of the data depending on the solution you have developed. For example, it could be that you are required to give a certain set of waypoints that you would like to go through, going from Moratuwa to Colombo. So you got like to go through Dehiwala and maybe Kolpiti, like that. And whether you need, whether such waypoints can be just given randomly, or whether you have to give them in a particular order, maybe in the order in which you would encounter them, which would be actually a bit more difficult then, because then you have to know the particular order along the path. Okay, so we have to consider all of these aspects in reviewing the algorithm, and then we might find that the algorithm does not meet certain criteria. Then you may have to go back to step 4, or even may have to go back to step 3. Because if some of the problems you see in the algorithm when you review can be solved by further refining, then you go back to step 4. But if a major change is required to the solution that you have developed, the algorithm will have to undergo significant change. So you will go back to step 3. Okay, so remember that algorithm development is an iterative process. Oh, before I forget, you must also remember it is quite possible when you are reviewing the algorithm, you find that you have misunderstood the problem. Then you may have to go back all the way to the initial state. Now, we will have a quick review of these steps. So in step 1, as I mentioned, the client will tell you what the problem is. Okay, and the programmer, essentially you, will have to record it as accurately as possible. Okay, so in the field of software engineering, we normally call the person who does this work as a system analyst. Okay, in the software engineering domain, in that field, that is the job description or job title of the person, a system analyst. But in our case, we can think of that work being performed by a programmer. Now, this is actually quite a difficult task, because the client could be very knowledgeable about the problem, because it's the client who had the problem. Okay, so it can be from different domains like stock management in a manufacturing company, okay, or vehicle fleet management in a company that provide transportation services, or I'm sure you have heard of a company called London Stock Exchange Group, one of the biggest software companies in Sri Lanka, which develop software for the financial markets, stock traders, like that. And the people who come to get software developed by them actually own and operate stock exchanges, so they know how that business works very well. But as a programmer, you may have only a limited knowledge in that particular problem domain. So this is one reason why you may not achieve the level of accuracy that we expect in recording the problem or documenting the problem. Okay, so so the client will make a best effort to share all the information with the programmer, and the programmer will make a best effort to record it as accurately as possible. But we have seen in the field of software engineering that this task does not end very well in quite a significant fraction of the time. Okay, why is that? What is the difficulty when you what are the difficulties you encounter when you are creating problem descriptions? So one is the assumptions. Okay, so generally the person telling you the problem would have certain unstated assumptions, because it does not come to the mind of your client to tell these assumptions. It is in their mind, they know about it, but it doesn't get communicated to you. So this is a very common problem, the common problem of unstated assumptions. Okay, so so that would lead to an incorrect understanding. So the program will not have a correct understanding. Second issue is the ambiguity. So the client brief the programmer on the requirements, but generally it is done either verbally or through written text, which is more descriptive. So it is not like giving it using a mathematical equation or an annotated diagram, which are more precise actually. But if it is given verbally or through descriptive text, the programmer will misunderstand it, okay, and misinterpret the description and will lead to ambiguity. What is an ambiguity? So client thinks this is what I told the programmer. Programmer thinks this is what the client told me, and the two things are different. So that's an ambiguity. Third, sometimes not all the details come to the programmer. One reason is when you are very much knowledgeable about it, like the client is very much knowledgeable about the problem, the client may not give all the details, and only the client might focus only on certain parts of the problem. So this incomplete detail also would lead to a wrong understanding by the programmer. And there may be contradictions ultimately that the programmer document as the requirement. So contradictions are basically requirements that are specified as part of the problem that does not tally. So these kind of contradictions would make it very difficult ultimately to develop a good understanding of the problem. For example, if you just recall what I told you about the finding the path from University to Colombo, and if you want to mark certain waypoints, say you want to go via Deivela and again say Kolpiti, now it may be a contradiction while giving these waypoints. You are also saying I need to go in the shortest path possible, okay, because the shortest path may not allow you to go through all of these waypoints, maybe one, maybe all of them, or maybe somewhere in between. Okay, so there may be contradictions. So if the client said no, I would like to go through these waypoints if possible, then that is okay, because you will No, you'll find the shortest path and we'll say, okay, you gave 3 waypoints, 2 of them are here in this shortest path that we have calculated for you. So, so there could be internal contradictions that would make it difficult in the solution building process. So the step 2 we discussed, the analysis step. So there are 2 key objectives. Okay, so the first one is, what is the starting point to solve the problem? This is always very important, where to start. Okay, and then the other very important point, how do we know we have solved the problem? That is the ending point. Okay, starting point obviously is to get the solution making process started, and ending point is to know that you have solved the problem. Okay, so it may not be that obvious that you have solved the problem. In many problems we are faced with. Okay, so we have to as part of our analysis, focus on these 2 key objectives and decide, okay, when this particular condition is met, our work is done. Okay, so let's say that a programmer is looking to find starting point. Then there are certain things the program will look for. Okay, so for example, what's the data? Okay, what's the data given to this problem and how they are given? Okay, for example, in the finding a root problem, one set of data would be the static set of data, the grid locations of the various nodes and the links between different nodes, because not every junction can connect to every other road. No, so what are the connecting roads? So those would be fairly static, of course. No, when new roads are being built, existing roads are closed for certain reasons, all of that can change, but generally you can think of it as a fairly static set of data. But when it comes to, say, the traffic congestion, that is dynamic. So that data may come to you only when you are actually trying to solve the problem. So you have to dynamically, okay, in real time acquire that data. Other data, it is available, statically available. Okay, so these kind of issues you must look at. What are the data available, how they are given, and then you have to look at different theorems, okay, equations, formulas, and similar type of theory that you can use with this kind of problem. So as I said, the pathfinding problem is essentially traversing a graph. So immediately you can think of the techniques available from graph theory. The vertices, the edges, and various algorithms we have to traverse such a graph. Then we have to also look at, in the problem description, there may be certain rules that impact the data. Okay, for example, if we have said that in toll roads, the amount charge will change based on the time of day. Say during peak hours, the road toll is higher. That would encourage people to actually travel in other times. That's the reason. Okay, so maybe the toll charge by a route is changing to a higher charge at 5 p.m. Okay, at 5 p.m. So up until 5 p.m. The charge is less. After 5 p.m. charge is higher. Now suppose you start your journey at 4:30. Okay, so at that time you may have not reached the road segment where you will be charged, and the charge is lower. But by the time you get there, it may be past 5 o'clock and the charge is now higher. So any previous calculation you have done to get the lowest cost path is now wrong. So you have to be mindful of this kind of issues that affect the data, the rules that affect the data. And among the data also, there may be certain relationships. So you have to study those things. Okay. Now, of course, in the path planning problem we have discussed as an example, there are relationship anyway between certain data, like the nodes, the vertices, they are linked by edges. Those are the road segments. Okay. And the relationships like that, and there are other relationships. For example, maybe there are certain paths which are circular. Okay, so so you don't want to get into a route that will endlessly keep you going round and round in circles without getting you to the destination. So you have to be mindful of these routes, as well as when you go towards Colombo, some roads are one way. Okay, so there are relationships between roads, where certain roads are the opposite road of another road. Okay, so that those are relationships among data that you want to be mindful when developing your solution. And those are for the starting point. And for the ending point of the problem, the program will look at things like, what kind of new information have I created? So in the previous lecture, you have discussed this, giving input, processing, and then getting output, and how what we give as input we call as data, and what we get as output we call as information. So data to information, and then again you were introduced to the fact that information that were output from one stage would be the data that goes as input to another state. Okay, another stage. So so we have to, so we'll be creating this type of new information, and we have to study that. That would allow us to figure out what is the endpoint and whether we have reached the endpoint. And the changes that occur, okay, in the system. Okay, for example, when you are traveling on a road, you are contributing to congestion. Okay, so the fact that now you are on the road should also now get into the system when congestion is being calculated. Okay, so that's a change. Okay, how is this change represented? Where is this data kept? Okay, so the number of vehicles that are present in a particular road segment must now be found and processed to determine a congestion value. Okay, maybe like an index value, 10% congestion, 90% congestion. Okay, like that. So study of these aspects will also help us determine the endpoint of our problem. Also, certain things that were present at the beginning will not be present at the end. Okay. For example, suppose you have, okay, I'll give a different example. For now, suppose you are sorting set of data items. So initially you have a set of, say, names which are not sorted into the alphabetical order. You still have the names, but at the end that random order is gone. Okay, random order is gone. So the removal of a random order and getting them into the alphabetical order is what you want to achieve if your intention is to sort some data. Okay, so like that you have to look at this kind of aspects. Okay, what's the new information created, what are the changes that occurred, and what are the things that does not exist anymore, as pointers to figure out whether you have reached the endpoint. Then the three steps at the end of our 5-step process, which is about the algorithm development, okay, to solve the problem. So in this task, we generally go about doing it in iterative manner and keep on adding details. So the whole process is a stepwise refinement. Okay, so an incremental improvement to an initial solution. So if you study this area in greater detail, you will find there are other ways of developing algorithms, but this is a fundamental approach, a very common approach to solve problems and come up with algorithmic solutions, the stepwise refinement. So to do this task, the program must gain all this information that we have discussed earlier, and the information must be accurate, unambiguous, complete, and that would allow for a more precise algorithm to be developed. And then the programmer will have to develop a computer program. Okay, ultimately this algorithm has to be converted into a computer program that you can execute on a computer. Okay, so depending on the environment, which is the operating system, and the hardware system on which it is running, and the other constraints you may have based on the development environment, you will use a specific language. So for our work, of course, we are using this Python language, which does not actually give highly efficient program code in terms of speed of execution or memory usage, but it is a programming language which is quite easy to understand when you write an algorithm using that. So you get your algorithm and you convert it to program. So your algorithm, the description of your solution, the precise description of solution, which is the algorithm, and the Python program would be quite similar. Okay, so this is going to help us see whether we have done our job of translating the algorithm to a computer program, whether we have done that correctly. Okay, so finally, according to our agenda, we want to discuss the process of modeling a solution to our problems. Okay, so we have this concept of abstraction. Okay, in this work we do to develop algorithms, we use the concept of abstraction. Okay, so what is abstraction? So the abstraction is, given any kind of issue, we would only focus on the core detail. All the other ancillary or additional details which are not necessary for us to have a thorough understanding of what's at the core, we are going to remove. Okay, so this task of simplification. Okay, so mind you, when we simplify, we don't get rid of important detail. We only get rid of detail which is not important for the core problem we are trying to solve. Okay, so this abstraction is a powerful concept. Okay, when you don't have all this detail that you can do without, you don't get distracted. Okay, so you will focus on the core problem. And also you will not get constrained by this additional detail. For example, now if you take the finding a route, as you know, road closures happen due to construction work, accidents. So if you take finding a convenient path to go from University to Colombo, while you're on the road, there could be a accident that causes severe congestion on the road. So that we are not going to focus on the accidents. We are only going to focus on the congestion rather than focusing on how the congestion has happened, whether it is due to an accident or whether it is due to more vehicles on the road due to that time of day. Maybe the officers are closing or things like that. We only focus on the congestion, the number of vehicles on a particular road segment as an index value. That's what we would call congestion in this case, and we only focus on that, and we don't get distracted by all this, whether there is a road construction work going, accident happening, a policeman directing the traffic to a different path. Like that, we are not going to focus on all that detail. Okay, so this kind of approach is required when building this abstraction of a problem. So on the most important details are what we are looking at. Okay, so this is a skill you have to develop. Okay, to focus on the important or core details. Another concept we use in problem solving is this computational thinking. Okay, so this abstraction is part of that very important approach to problem solving, which we call as computational thinking, and it consists of 4 sub-concepts. Okay, abstraction, decomposition, pattern recognition, and algorithms. Okay, so all of these are part of our problem solving toolkit. So you can think of yourself as a problem solver who has a toolkit. Okay, so abstraction is one such one tool in that toolkit. Okay, it is a capability you have developed where when given a problem you will look at only the core detail, not get distracted by ancillary issues. Second one is decomposition. When given a problem, a composite problem, okay, you are able to engage in a decomposition task where the problem can now be broken into parts. So when you break this into parts, it may be, it could be of different type of breakage. So sometimes you might be able to say these things that need to happen are quite independent to each other. So you can separate out the problem into sub problems, or you find that bigger problem consists of a sequence of sub problems. Okay, so kind of a hierarchical decomposition. So like that, decomposition is also another approach to thinking about developing a solution. Okay, mind you, thinking about developing a solution. Third one, pattern recognition. Okay, so in pattern recognition, you will look at your problem and you will see certain patterns that will remind you of certain other problems which you may have already solved quite efficiently and elegantly. So then you may be able to adapt those solutions to this particular problem that you are trying to solve now. Okay. Finally, algorithm. So you might wonder why algorithms, term algorithm is already here again, because coming up with a refined solution that is precise is what is an algorithm. So the algorithm here refers to certain standard solutions we have. Okay, standard solution. So for example, that graph traversal is one such standard solution, and there are other standard solutions such as sorting, searching, where you have well established algorithms that can be part of your toolkit. Okay, so again, just to summarize, computational thinking consists of 4 different tasks that you will engage in when developing a solution to a problem which is not trivial. So the problem has to be fairly complex, and you will engage in these tasks when developing the solution. Next, the abstraction, mind you, the abstraction only gives you a general idea of the problem. And in fact, if you start with the abstraction and create a solution, the solution will also be only general. Why? Because when we abstracted the problem, we got rid of all the special parts in the problem that make it unique. Okay, so this is only a general idea that you get with abstraction. Okay, so to get the actual solution, you will have to keep on adding back those details that made the problem to be specialized. Now, as we have removed the specific details and any patterns that are not required to come up with our general idea or the general solution, this is really an abstract solution. Okay, so another term we use for the abstract solution is the model. Okay, so here the greater understanding of the problem is the first step of our solution. Okay, so we try to build a model of the problem by getting rid of all the detail and getting rid of all the unnecessary detail and just leaving only the essential parts. So this first level of problem that has been abstracted is the first step of solution. So this would allow us to go towards building a solution that our client would accept. Okay, mind you, a solution based on the abstract idea will not be acceptable to the client, because client has a very specific problem with all the detail. So ultimately we have to solve that problem which the client has. Okay, so just to summarize, this fairly accurate generalized idea of the problem is what we call the model. Okay, so with these problems that we are faced with, the more complex the problem, greater effort we are going to put to make it into an abstract model, because the complexity needs to be tackled. So when you have a very complex problem, you will not find it easy to come up with a solution until you bring it to a level of abstraction that helps you to understand it. Okay, so we'll be dealing with multiple levels of abstraction. So so at some point you might have only a small set of detail which are the core detail of the problem, and that would be one level of abstraction. Then you would add some other details which are essential to make it a problem that is meaningful to the client. So that would be another level of abstraction. So like that, you will be required to keep on adding details also. Okay, otherwise you will not be able to develop a solution that the customer would be satisfied with. So when you have these multiple levels of abstraction, it has a very advantageous outcome, because that will allow us to see, okay, at this level of abstraction, I have seen this problem elsewhere, which has a good solution. Then you can reuse that solution. Okay. So reusing solutions is an important task for engineers. Okay. Engineers must look to reuse. It's very important. Because that would lead to solutions which you can develop faster, cheaper, and more reliable, because a reuse solution would have been tested previously, so it has higher reliability also. And sometimes you might find the solution that you have in a different but similar problem is not directly usable, but then we can modify and adapt it. Okay, so that will also reduce the effort and resources you have to put to develop a solution. So I have an example here. Suppose we have a solution, an algorithm to sort numbers so that they get listed in increasing order. Now, if we want to sort a different kind of data, say strings, that means names, for example, which you want to sort into alphabetical order, we can use the same algorithm. Only difference is, earlier we were using numeric data, now we will be using character data. Okay, so so this abstraction has quite useful outcomes in that manner. Okay, so that concludes this discussion on problem solving, and I have left an exercise for you to do as a task of problem solving. Okay, so please read the question given and think of a solution, but use the technique I have given. Okay, so don't try to focus on solving this specific problem, but think about based on the set of steps I have discussed with you now on how you can go from a problem description given to you to a precise solution, the algorithm which will solve the problem.